Electric force is conservative, so we can say that the change in the kinetic energy is equal to minus change in potential energy, as we have done so many times before. Now, change in potential energy is Q delta V, and change in kinetic energy is 1/2 m V final squared minus V naught squared, as we know from doing that a million times. So we can solve problems using the conservation of energy. Let's say we have an electron that is initially at rest, placed in a uniform E field with magnitude 1.2 times 10 to the 4th newtons per coulomb, and we want to know what is its speed when it has traveled 1.3 millimeters. Now, the first question to consider about this, this delta V, the signs of things are going to be important when we deal with this delta V, because we know delta V is minus E delta S. But delta S is positive in the direction of the E field. Okay, so this becomes Q E delta S. All right, so if we just start plugging values in, we got 1/2. Electron has a mass of 9.1 times 10 to the minus 31st kilograms, which you can find on the inside back cover of your book. The mass of the electron is listed there. And then its V final is what we want to know. Its V naught is 0. And that's equal to Q. Well, its Q is negative 1.6 times 10 to the minus 19th. The electric field is 1.2 times 10 to the 4th. And our delta S is 1.3 millimeters, which is 0.0013. But this is an electron, which means that if the E field is pointing to the right, the electron is going to move to the left, and since that displacement is in the direction opposite the electric field, it's a negative 0.0013 millimeters. Therefore, negatives cancel out and we have a positive, which is good because then we get a real number for every final instead of an imaginary. And we can type this in, 1.6 times 10 to the minus 19th times 1.2 times 10 to the 4th times 1.3 times 10 to the minus 3rd times 2 divided by 1.1 times 10 to the minus 31st square rooted. And it turns out our electron has a very large final velocity, 234,216.175 meters per second, which kind of makes sense because an electron is really, really, really little. Right? And we could, set up other sorts of conservation of energy problems, but the key thing is always going to be this delta KE equals minus delta PE. And depending on what you're given, it's either going to be this version or maybe you'll use QE delta S. Right? Here's a question. Let's say a proton and an electron accelerate through the same potential difference. Which winds up with greater speed? Think about that for a second, see what you come up with. We know this change in kinetic energy is equal to Q delta V. And the Q and the delta V are the same here. So the delta KE of the electron is going to be the same as the delta KE of the proton. But we know that kinetic energy is 1/2 mv squared, and the mass of the proton is much larger than the mass of the electron. Therefore, the velocity of the electron is going to be much greater than the velocity of the proton. So make sure you consider the sizes and not just or the masses, I should say, and not just the charges. Right? Now we know that our electric field, we're going to look at point charges here. Point charges. We know the electric field of a point charge is kq over r squared. We also know that electric field is dV by ds, right? with a minus sign. K dV by ds with a minus sign. So if we, in this case, in the case of a point charge, this displacement in the direction of the electric field can also be called the radius, the distance from the charge. So this electric field, kq over r squared, is equal to minus dV by dr. And if we go ahead and do an integral to get an r squared, that's a 1 over r. If we take a definite integral from two different points, from r2 to r1, we get a kq over r2 minus kq over r1. Because if we take a derivative of minus kq over r, we would get positive kq over r squared, and then the negative out front turns it back into just kq over r. So this is kq over r2 minus kq over r1, and that's equal to our potential for a point charge, for a change in potential, I guess. And typically, remember, we could set the 0 wherever we wanted to. So we say that we set this r1 equal to infinity, and then we can just say our potential is just kq over r. And we know that our potential energy, out of space here, we know that our potential energy is equal to qv, and therefore, when we add another charge, I'll call this q2, I don't know, it becomes k, q1, the product of the two charges, over r for our potential energy. And potential energy both add up. So for example, let's say we have charges of 1.3 microcoulombs and minus 2.4 microcoulombs are placed at the origin, and 3 centimeters, 0, respectively. And I want to find the potential at 0, 4 centimeters. Potentials add up, but they're not vectors. So the total potential is just the sum of the potentials, which is k q over r. So we've got k 1.3 times 10 to the minus 6 over r. It's at the origin, so our r is just 4 centimeters, plus k times minus 2.4 times 10 to the minus 6 over r, but this is at from 3, 0 up to 0, 4. Well, this is a 3, 4, 5 triangle, so this hypotenuse is 5. So that's over 0.05 squared. And we can add those up to get our potential. So k negative 6 times 1.3 over 0.04 squared minus 2.4 over 0.05 squared. And we get a potential of minus 13.26, that many volts. Right? And that kind of makes sense. You know, for our potential energy, we set to 0 at infinity. As you get closer and closer to this negative charge, the potential is going to drop, and this negative charge is bigger than this positive charge. Likewise, potential energies add up. Say we want to find the potential energy of charges 2.0 microcoulombs, 2.5 microcoulombs, and minus 3.1 microcoulombs, situated in an equilateral triangle with side 5 centimeters. We can do this. If we want to find the total potential energy of an arrangement, it's the potential energy of each pair of point charges all added up. right? So we can just punch that in. We've got K times 2.0 times 10 to the minus 6 times 2.5 times 10 to the minus 6 over the distance between them is 5 centimeters, 0.05 squared, plus K times 2.0 times minus 3.1 times 10 to the minus 12 over 0.05 squared plus K times minus 3.1 times 2.5 times 10 to the minus 12th over 0.05 squared, and we can add those up and find the total potential energy of our charge distribution, which comes out to minus 32.1842 joules. That's how we can deal with potentials or potential energies when we have charge distributions. We just keep adding them all up.